Okay, let me start. So today this is the last week of materials. And then the first thing we're going to discuss is optimizations. But to be honest, optimization is not really a new topic. That is, we try to learn how to find the absolute maximum and absolute minimum. Okay, find of a given situation. But previously, if I ask you to find absolute maximum and absolute minimum, I may just give you a function and a closed and bounded interval. Then you just compare the values of f at the critical number and the boundary point and see which one is the largest. What is different here? It's just slightly different. The only difference here is you are given a story to read. Okay? So you have a story to read, and then from this story, you write down by yourself the function you try to optimize and compute that. So that's the only difference. So what we want to test you here is not mathematics, but your ability to read English. Okay? And obviously, it's not a problem for you guys. You take the English class, right? Reading English, easy. Okay? Okay, let's have a look. Okay, let's have a look. The figure below shows an isosceles triangle. Now, very difficult English, huh? Isosceles. I learned this term a few weeks ago, okay? Okay? So that means that two of the sides are equal. Here, we give you that AB equal AC. So AB and AC are equal. And then you're given BC is 4. Okay, BC is 4. And what else you're given? You're given here AD equals to 3. That means that this height here is 3. And then PD equal to X. And then what is R? R is PA plus PB plus PC. So is PA. Let me use the thicker pen. PA plus PB plus PC. And then where x, okay, because x is the length of something, therefore x has to be greater than or equal to 0, and then, at most 3, because this length is 3. So you're given a domain for x. So this one is a domain for x. And then what's the question? The question is find the greatest and least value of r when x varies. So you want to optimize the function r. So of course, the first step is to firstly actually write down what r is. But r is what? R is PA plus PB plus PC. So let's write that down one by one. So firstly, PA, the difficult geometry, D is 3. D is x. So PA is 3 minus x. Okay? And then PB. PB, firstly, we realize that PB by symmetry should be the same as PC. And moreover, what is PC? PC is the length of the hypotenuse of this right angle triangle. So D is 2, D is x. Therefore, D is 4 plus x squared, square root. So this is really the square root of 4 plus x squared. Hopefully not too difficult, right? Okay. You can get through this. So hence, what is R? R equals to PA plus PB plus PC. So you have 3 minus x plus this guy, but twice, okay? Twice square root of 4 minus x squared. And sometimes when you have no sense of humor, you can emphasize that this is not just r. There is a function in x, so r of x. And our goal is to optimize this function r on the interval, okay, on the interval 0 to 3. So how do we do that? Well, once you write down a function, it gets back to what we learned previously. You just compare the critical numbers and the boundary point. But to do this, firstly, of course, I need to compute the critical numbers. So let me differentiate that. So critical numbers. To find critical numbers, we're going to set r prime x to be 0. Then if you differentiate correctly, then you will get -1, and then I think, okay, let me, why, plus, no wonder it looks fancy to me. Sorry, plus, it's a plus. I don't know what happened to my mind. Okay? But can you learn a habit? Whenever you do something crazy, you shout, okay? You shout whenever you do something crazy. So if I differentiate correctly, then I will get 2x over the square root of 4 plus x squared equals 0. Please check, okay? So in particular, -1 plus a fraction equals 0. That means that this fraction equals to 1. This fraction equals to 1 means the numerator equals to the denominator. So 2x equals to the square root of 4 plus x squared. And then to solve this equation, we rely on, we square both sides to obtain 4x squared equals to 4 plus x squared. So we get x squared equals 4 over 3. That means x is either 2 over root 3 or x equal to minus 2 over root 3. But however here, you realize that because x is representing the length of something, in particular x is between 0 to 3, so you can ignore this point. This should be rejected, as x is between 0 to 3. Okay? So you really just get one critical number. That is 2 over root 3. And now you just need to compare. Compare what? Compare the function at the critical number as well as the boundary. In this case, I only have one critical number. That's 2 over root 3. And then I have 2 points at the boundary, namely 0 and 3. So this is the critical number, and these 2 are the boundary. Plotting a number into a function, hopefully you have no trouble, so I will let you to check. The first one should be 3 plus 2 root 3. When you plot 0, okay, when you plot 0, so 3 minus 0 is 3, and plus 4, so 7. And finally, when you put 3 inside the last one, then 3, so you get 2 square root 13. Now the actual challenge comes, okay? The actual challenge comes. I know that the largest one will give me the absolute maximum, and the smallest one will give me the absolute minimum. Which one is the largest? Like, don't forget, you are not allowed calculator, okay, in the exam. So without a calculator, can you tell which one is the largest and which one is the smallest? Oh, okay, let me start with 2 of them, okay? These 2. Which one is larger? 7 or 2 root 13? 7. or 2 root 13? Eh? 2 root 13, okay? Because this one is square, this is not university mathematics. Huh? This is square root of 52. This is square root of 49. Therefore, alpha, oh, really? Really? So alpha is greater than, strictly greater than L of 0. Secondly, this two, which one is larger? The first one or the second one? The second one. That's the reason why I write it like this, right? You just need to compare this part. And then square root of 3 is less than 2, so D is less than 4. Therefore, use whatever method you know without a calculator to determine this, please. But once you identify which one is the largest and which one is the smallest, using the result that we learned last week, then this one will give me the absolute maximum. And this one will give me the absolute minimum. So we are done. Okay, so this is the first example of optimization. It's theoretically, there's nothing new, but then now you have a story to read and then write down by yourself the correct function to optimize. Okay, let's move on to a different example. The figure below shows a straight wall, okay, straight wall AB of 8 meters. So this is 8. The length here is 8. Resting on a vertical wall of height 1 meter. So this is the vertical wall, 1 meter. And then NB is free to slide along the horizontal rail, blah, 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 okay? But the key is you have a length x here, you have a length s here, and there is a domain for x. X is between 1 and 4 root 3. So there's a domain for x. And what do you want to show? Okay, part A, show that S can be written in terms of x, is a function in x in this way, and find the maximum value and minimum value of S. So we need to make some connection or some relation between S and X. But what's the idea? The idea is that, this again, not university mathematics, but you need to be sensitive about this. Whenever you see a bunch of triangles, then the technique is to compare similar triangles. I also learned this a few weeks ago. Okay? I mean the Chinese term, the 中文 term. Okay? So you realize that there are two triangles, they are similar to each other. This is firstly the small one over here. Secondly is the large one over here. So let me do it one by one. So part A. So by comparing similar triangles, which two similar triangles? The first one is the small one over here. So it's the small one, and there's a big one. Let me draw it prettier. The small one, what do we know? We know that the base is x. The height is 1. And elementary mathematics, Pythagoras theorem, tell you that the hypotenuse equals to square root of x squared plus 1. And it's similar to the larger triangle. What do I know about the larger triangle? The base is s plus x. And then the hypotenuse is given to be 8. Therefore, if I compare the ratio of the length here, they should be the same because they are similar triangle. So hence, we have the square root of x squared plus 1 over x, so equals to h over s plus x. But of course, if you rearrange, then you get s plus x equal to hx over square root x squared plus 1. So consequently, s equals to minus x plus 8x divided by square root x squared plus 1. But as I've previously have done, sometime when I have no sense of humor, then I will remind myself there's a function in x, so s of x. And also, don't be too funny. This and this are the same, okay? Don't say that, oh, they are different. They're the same, okay? Please. We obtain part A by just elementary geometry. And now we come to the actual calculus part, that is optimize this function here. And as usual, to optimize this function here, we're going to use, compare the values at the critical number and at the boundary. So let's compute the critical numbers. Critical numbers. To compute critical numbers, we are going to set the derivative of s to be 0. Okay? So, but we know that s prime of x, if I differentiate correctly, you will get minus 1 plus, okay, a is a constant, I don't touch it. To differentiate this guy, do it slowly with quotient rule, then you will get 1 square root of x squared plus 1 minus x, and then I think you will get x over square root of x squared plus 1, and then divided by x squared plus 1. Check, okay? My TA told me that some of you get stuck in differentiation. Then how do you survive your physics? Or you didn't? I don't know. We're curious about this. But let us know if you really get stuck in differentiating things correctly. So don't forget any chain rule or anything like that. Okay? But before I move on, you realize that, oh my dear, okay, this derivative is a total mess. But the reason why it looks like a total mess is because of this denominator here. So the trick, okay, is to clean up the denominator by multiplying both the numerator and denominator by x squared plus 1 square root. If I do that, I will get minus 1 plus h times, okay, firstly, a fraction, and then the denominator is x squared plus 1 to the power 3 over 2. You will see that there will be magic happening in the numerator. Firstly, square root times the same square root become x squared plus 1. And the minus x squared plus 1 square root at the bottom times this, so they cancel. So you get x squared. So initially, without doing this little trick, you may have a nasty mess, okay? But after you do this, you get a much simpler derivative. So, if, okay, f prime x equals 0, that means that this derivative equals 0, but this derivative is minus 1 plus something. For it to equal 0, that means that this fraction should be 1. For this fraction to be 1, I need the numerator and denominator are the same. So, I will need x squared plus 1, 3 over 2 equals to 8. I hope I won't annoy you by doing some baby mathematics here, okay? Because in the past, I got students getting stuck in this. They don't know how to solve this. So let me do it. Take the power 2 over 3 from both sides. H is 2 to the 3. So this becomes 2 to the 2, become 4. Therefore, okay, the left-hand side, 3 over 2, 2 over 3 cancel each other, so you get x squared plus 1 equals to 4. That means x is either root 3 or minus root 3. But as previously indicated, x here, again, is the length of something. In particular, x is between 1 and 4 root 3, so you should reject the negative one. Okay, reject the negative one. So again, you get only one critical number in this case. And once you obtain the critical number, you just need to compare with the boundary point to figure out which one is the absolute maximum and minimum. So compare as of, okay, the boundaries are 1 and 4 root 3. And then you have one critical number that happens at square root of 3. So these two are the boundary. This one is the critical number. And you have already computed a function in S, so you just plug this number in, and I will let you to check the outcomes are respectively -1 plus 4 root 2, and then 3 root 3. And then the last one, the other way around, sorry. 3 root 3. The middle one is 4 root 3 over 7. But I will give you a challenging exercise to do tonight. Check. Without a calculator. Don't say that, I do it with a calculator, okay? Check. 3 root 3 is largest. -1 plus 4 root 2 is in the middle. And then 4 root 3 over 7 is the smallest. Please check it tonight by yourself. Without a calculator, find a way to do it. If you get stuck, of course, come to my office hour. I will tell you how to do this without a calculator. So that means that the largest one here, okay, the last one, will give me the absolute or global maximum. And then the middle one will get me the absolute minimum. And we are done. Okay. Next page is a continuation of this example. So what happened now is that, okay, the same situation, but what you look at is something different. You're going to look at the area of the trapezium. So you're going to look at the area of this object here. The area of the trapezium CAED. And the part 1, of course, firstly, write down the function P, okay? Write down the function P. P is the area of CAED. But think about what you want to prove at the end. What you want to prove at the end is an expression like this. It's something minus something. So you probably can imagine that instead of computing this directly, you should, write this as a difference of two areas, namely the area of the larger triangle minus the area of the smaller triangle. So area of AEB minus the area of CDB. And now it becomes elementary geometry. The larger triangle, the area is a half times s plus x times the height. What's the height? I'm not sure, but let me write down just AE, the length first, okay? And then minus the area of the smaller triangle. But the smaller triangle, the area is easier because it's just x over 2. Okay? But at least you can tell yourself that you should be on the right track because it looks quite similar already. Okay? What we need to do is to make sure that the first part equals to 32x over 1 plus x squared. But how do we do that? Well, I mean, You can compute AE in a horrible way, like because this 8 and then s minus x, and then you can do Pythagoras theorem. Or the reason why you learn similar triangle when you were a baby is because, okay, you can do similar triangle again. If you look at the smaller triangle, you get 1x here. If you look at the larger, okay, the larger triangle, you get s plus x. Sorry, s plus x, and then the height is what we wish to find, namely AE. So by comparing similar triangle, then we get 1 over x, so equals to AE over s plus x. So AE equals to s plus x over x. But think about that. In part A, you have computed what is s plus x. Look, I will turn for you. You don't have to turn. In part A, you show that s plus x equal to ax over square root of x squared plus 1. So this turns out to be just 8x over x squared plus 1, but don't forget you have an x at the bottom. But of course, okay, this and this cancel each other. So AE has a very pretty looking expression. So hence, okay, hence, s plus x, by part A, we know that this ax over square root of x squared plus 1. AE, idea above, that is h over x squared plus 1. This by A, this by above, and then minus x over 2. So after you simplify, you get what you want. You get 32x over x squared plus 1 minus x over 2. But what is interesting is actually the final part, okay? The final part is to make connection between part A and B. They ask you whether if this length is maximized, is it true that the area here is also maximized? Now, being a skeptical person at NTU, you should always be critical and think that this should be no, okay? But you need to explain why, okay? If someone say that, oh, something seems to be true, it's no, okay? It's no. Okay, but we need to explain why. How do we do that? Firstly, before I do anything, just to recall from A that S attains its maximum value when x equal to root 3. Okay, we know that S attains its maximum value when x equal to root 3. This is the result that we find in part A. And we're wondering whether at the same point, P will also attain its maximum value. Okay, to do that, let us differentiate P. If I differentiate P with respect to x, so P is over here. P is over here. Let me differentiate that. I will get 32. And then, okay, quotient rule 1, x squared plus 1, and then minus x, 2x over x squared plus 1 squared, and then minus 1 over 2. It sounds like my neighbor's dog. Okay. Okay. But we want to see whether x equal root 3 will be a maximum point for P as well. So let's have a look. What happened to its derivative? When x equal root 3, you put the inside, you get 32, okay? Root 3 squared plus 1 is 4, minus, okay, let you check 6, and then at the bottom you get 16. Minus a half. So you get minus 4 minus a half. Hopefully, you don't need a calculator to realize that this is not 0, okay? So that means that, okay, hence, the point x equal root 3 is not, okay, it's not a critical number for P. This is not a critical number, moreover, also not a boundary point, a boundary point. But we have learned that to attain a maximum value or minimum value, it has to be either at the critical number or boundary point, and this is not the case here. Therefore, P does not attain its maximum value at x equal root 3. Okay, so that's the idea. So you realize that this point is not a critical number for P, and also it's not a boundary point, and we've learned that the only way to attain extreme value is either at critical number or boundary point. And they are, or at this point, with 3 is neither of them. So you cannot obtain maximum value there. Okay, so after this, we'll start our final topic of Calculus 1. That is L'Hopital rule, the actual L'Hopital rule. But before I do that, I would like to mention one more version of MVT. That is the Cauchy MVT, okay? Cauchy's MVT. Cauchy is a human being. Hopefully you know that. So, in the previous version of MVT, we analyzed only one function, f, okay? And I tried to analyze the slope of secant line and realized that that should always equal to some slope of tangent line at some point. And the Cauchy MVT is different in the sense that it can deal with two functions, not only one. So you have two functions, f and g. And the standard condition, you need they're continuous on the closed and bounded interval and differentiable on the open interval. Then what does Cauchy MVT tell me? Cauchy MVT tell me that then fb minus fa divided by gb minus ga is f prime c over g prime c. So the difference between this version and the previous version of MVT is that this one involves two functions, not only one. But how do we do that? Okay, how do we do that? So there's a magic here. Cauchy come up with a very fancy function. Cauchy consider this function h of x equals to f of x minus fb minus fa over gb minus ga times gx minus g of a. Firstly, don't be too scared. Where are the x? X is here, here, and here. So all the other numbers that occurred, are just constant. They are numbers, okay? They are numbers. So in particular, if you differentiate h, you should get f prime x, and the minus, don't be scared by the constant, okay? Constant is constant. And then g of x, when you differentiate, you get g prime x. G of a, when you differentiate, it dies, okay? It dies because it's just a number. So don't be scared of this horrible expression because most of them are just numbers. The only thing you need to differentiate is anything that with an x there. But I still haven't motivated why Cauchy come up with this function. What is so special about this function? So note, this function is special in the following way. If you put a here, if you put a, h of a, then of course you get f of a minus this horrible number, fb minus f of a, and then gb minus g of a. But then if you put x equal a, the last bracket becomes 0. So this is really just f of a. How about the other endpoint, h of b? If I put the other endpoint, then I will get f of b minus, okay, this horrible constant, gb minus ga. But then what is inside the bracket now is become also gb minus g of a. But that's a fantastic thing, you can do cancellation. Cute, okay? Then if you stare at it long enough, then you realize that it is f of a as well. So that's the motivation how Cauchy come up with this function. Because he come up with this function such that, so in particular, this function will agree at the endpoint HA equals to H of B. If HA equals to H of B, then by the ordinary MVT, then we have HB minus HA divided by B minus A equals to H prime C. For some C, okay, for some C between A and B. Some of you ask me, what does for some mean? For some, it's different from for all. For some things, for okay, English time, okay. But because we know that H of A equals to H of B, therefore the numerator here becomes 0. So we have H prime of C is 0. If H prime of C is 0, we calculate H prime above, okay? We calculate later H prime above, hence we have F prime C minus this horrible fraction FB minus FA divided by GB minus GA and then times G prime C equals 0. Now after you rearrange, okay, then you get this horrible fraction becomes your dream, that is F prime C over G prime C. And we're done. This is the Cauchy MVT. So why do I mention the Cauchy MVT here? Because for some of you, if you know L'Hopital rule, you realize that this looks familiar, okay? So it turns out one special case of the L'Hopital rule is a consequence of the Cauchy MVT. So as I mentioned here, Cauchy MVT is an essential ingredient to deduce a special case of L'Hopital rule. So let us turn to the next page. So which special case that I'm going to deal with? The special case that I'm going to deal with is called CO over CO case. So special case. CO over CO case, okay? So I need to assume a few things. The situation is the following. Suppose the limit of f prime x over g prime x go to a exists, okay? Let me say exists, or at worst, plus or minus infinity. So it won't be oscillating. We have to assume it's not oscillating. And then what am I CO over CO case? That means that I also assume f of a and g of a equals 0. Okay? And then I will use the Cauchy MVT to show you that in this case, I can deduce the L'Hopital rule. So what is the L'Hopital rule? L'Hopital rule concerns the limit of fx over g of x. But let's do it slowly, okay? So if I apply the Cauchy MVT, okay, then I have f of x minus f of a over g of x minus g of a equals to f prime c over g prime c for some c between a and x. For some c strictly between a and x. Okay, I didn't do any mathematics. I just write down the statement of Cauchy MVT that we discovered just now. But we assume f of a and g of a equals 0. So these two are 0. Okay, these two are 0. What we want to study is not only the fraction here, but how about if I take limit x go to a on both sides? Okay, let me write one more sentence, okay? Let me write one more sentence. Now we come to an interesting thing. The left-hand side, okay, fine. The right-hand side, okay, the right-hand side. What is the relation between x and a and c? What we know is c should be strictly between a and x. So for example, c is between a and x like this. And now what happens is x go to a. X get closer and closer to a. But c has to be between a and x. Therefore, as x go to a, c also go to a. Right? Because c is between x and a. And then if x get closer and closer to a, and c has to be in the middle, then c also get close to a. So hence, we have x go to a, fx over gx equals to the limit f prime c, g prime c, and then c go to a. Okay? And then we know that the right-hand side exists, so we are done, okay? D is the L'Hopital rule. So D is the L'Hopital rule. L'Hopital is French, so you can spell it like this. Okay? So that's why I mentioned the Cauchy MVT here, because you can deduce a special case of L'Hopital rule using the Cauchy MVT. So before I move on to doing examples of L'Hopital rule, I want to make two important remarks here. Remarks. Firstly, is well, here we only prove the special case where x go to a, and then the fraction is of the form 0 over 0. But there are versions of L'Hopital rule. Let me be lazy, I just call it LH rule, okay? That deals with either x go to plus or minus infinity, or the fraction fx over gx is of infinity over infinity form. The proof is not too hard, but then there's some trick, and I don't want to spend time going through here. Actually, the crucial ingredients is still the Cauchy MVT. Secondly, it's more important. That is, if you look at the above proof, for the above proof, at a certain point you realize that we take limit. Well, we take limit on both sides. But for this to make sense, you need at least one of them to the limits to exist, okay? So, for the above proof, for L'Hopital rule to be valid, to make sense, it's important we need the limit of the definitive version. We need this limit to either exist or at worst equals to plus or minus infinity. So in particular, what does that mean? In particular, that means that you can not use the L'Hopital rule to show a limit does not exist, or to be more precise, a limit is oscillating. So if whenever you apply the L'Hopital rule, the conclusion can never be your limit is oscillating, because the proof would fail. Okay? We see some misuse of L'Hopital rule later, but today we're going to go through a few standard examples first. Okay, let's come to the general statement of L'Hopital rule. L'Hopital rule. We actually mentioned that last time as a convenient tool to compute asymptotes. That is, whenever you get a fraction, and then you try to compute the limit, what happened? Is that okay? Okay. And then, if this fraction is of so-called 0 over 0 form, or infinity over infinity form, then you can apply the L'Hopital. What does that mean? That means you can differentiate both the numerator and the denominator to compute the limit. Okay? And then I make a remark here. We allow the a here and the limit here to be plus or infinity in L'Hopital rule. But we do not allow L to be something like oscillating, does not exist, that kind of thing. Okay, let us do an easy example. The first one. Compute the following limit. The first one is limit x goes to 0, and then the numerator is e to the x minus 1. The denominator is cosine x minus 1. To apply the L'Hopital rule, firstly, you should identify which indeterminate form it equals to. Is that 0 over 0 or infinity over infinity? So is that 0 over 0 or infinity over infinity? C. Good, okay? So in this case, it's 0 over 0. So L'Hopital. Now, L'Hopital is a word that I invent myself. It's not actual adjective. So if you apply L'Hopital, that means you differentiate both the numerator and denominator. Then you obtain the numerator. When you differentiate, you get e to the x minus 1. The denominator, when you differentiate, you get minus psi x. Okay? Now, I know some of you are very smart, and then immediately you can tell the limit is minus 1, but I'm very stupid. So I decided, well, I look at this fraction, I realize that this time is, again, of the form 0 over 0. So let me L'Hopital again. Then I will obtain e to the x, and then minus cosine x. But then now you can tell yourself to stop. Why? Because this is not indeterminate form anymore. You can compute the limits directly by plugging, okay, to obtain e to the 0 over minus cosine of 0. So 1 over minus 1. So the answer is minus 1. Okay? Don't just keep differentiating. You need to make sure that the fraction is indeed of the form 0 over 0 or infinity over infinity. Okay, let me do another example. limit x go to infinity of 1 plus x cube root minus 1 divided by x. In this case, you realize that this fraction is of the form infinity over infinity. So L'Hopital. So you apply L'Hopital. That means you differentiate both the numerator and denominator. Now let me do the easy one first. Differentiate denominator is 1, okay? And differentiate numerator, you will get 1/3, 1 plus x, and minus 2 over 3. Okay? So sometime after you do L'Hopital, you will end up with something nasty like this. So usually my habit is tidy this up a little bit. If you tidy this up a little bit, you will get 1 over 3, 1 plus x, and 2 over 3 at the bottom. But you can immediately tell as x get larger and larger and larger, the denominator get really huge. That means this limit is 0. So we're done. Okay, as x go to infinity, then the denominator get huge, so the limit is 0. Okay, so this is easy application of L'Hopital rule, but of course we don't let your life that easy. Okay, so we come to the next page, variance. So sometimes they have, well, you will have other so-called indeterminate form. So the first one is called infinity minus infinity. The other one is called 0 times infinity. So how do you apply the L'Hopital rule in this case? So the idea is very simple. So the idea is you try to converge them into either 0 over 0 or infinity over infinity, such that you can apply L'Hopital. So for example, if you encounter an expression of the form infinity minus infinity, then the usual trick is to take common denominator. And then, okay, if you encounter the second kind, 0 times infinity, then, okay, by the way, 0 times infinity is not 0, okay? So I saw some of you write something horrible in the semifinal. So, note, important note. 0 times infinity is not necessarily 0, right? E.g., limit of x go to 0 of x times 1 over x is 1. Okay? This is of the form 0 times infinity, but the answer is not 0. So be careful about that. Okay, if you encounter 0 times infinity, the way to do it is to rearrange into the ordinary indeterminate forms. There is the two fundamental forms, 0 over 0 and infinity over infinity. But talking about this sounds more difficult. Let us have a look on some concrete examples, okay? So, example 1. Compute the following limit 1 over x squared minus cotangent of x divided by x. So this is what we call when x go to 0, the first guy will go to infinity. The second guy will also go to infinity. And the answer is not 0, okay? The answer is not 0. We shall see. So as I mentioned, the way to do it is to take common denominator. So let us take common denominator to make it become x squared and 1 minus x cotangent x. But there is a slightly annoying thing here. Although, I mean, if you're smart enough, you properly can see, you can apply L'Hopital rule directly. But then if you cannot see it, because x equals 0 is not defined for cotangent. Because cotangent is cosine over sine. And then as x, well, you have a sine in the bottom. So as x goes to 0, the function is not defined there. So we would like to tidy this up a little bit by clearing the denominator to obtain at the bottom x squared sine x, and at the top sine x minus x cosine x. The reason why I do it is because now it's clear this fraction is of the form 0 over 0. It becomes very L'Hopital. Okay? So let me repeat. The reason why I clean this up is just because after I clean this up, I get a fraction that is more clearly is of the form 0 over 0. So let me do the L'Hopital. Let me differentiate the numerator, then you will get cosine x minus, okay, cosine x, and then so is that plus x sine x. Check, okay, check. So differentiate this by product rule correctly. You will get this. And then the other guy at the bottom, when you differentiate this by product rule, you get 2x sine x plus x squared cosine x. And then you realize there's a good news that is cosine and cosine kill each other. So you're left with x sine x over 2x sine x plus x squared cosine x. I know some of you are very smart. You probably can read out the limit already, but I'm an idiot. So I will realize that, oh, this is again 0 over 0 form. So let me L'Hopital again. If I L'Hopital again, then the numerator becomes sine x plus x cosine x. The denominator, okay? Oh, sorry, I can do one more thing. That is, there's an x that you can cancel, right? Sorry. There's an x that you can cancel. Then I actually get something a lot easier to differentiate. Then the numerator becomes just sine x derivative is cosine x. And then the denominator becomes 2 cosine x, and then plus cosine x minus x sine x. Okay? And now you can work out the limit by directly plot to obtain cosine of 0 over 3 cosine of 0 minus 0, which is 1 over 3. Okay, so this is the trick of how to handle this in infinity minus infinity. In particular, remember, infinity minus infinity is so-called indeterminate form. That means that you cannot read out its limits directly. You have to actually do some computation. And the answer is not 0. For example, in this case, the answer is 1/3, for example. Okay, the next limit x times log of sine x as x goes to 0 plus. Firstly, when you look at that, you realize that this is of the form 0 times, well, to be more precise, minus infinity, but let me just write infinity. 0 times infinity form. So it's one of the indeterminate form. That means we should handle it carefully by L'Hopital rule. But to apply the L'Hopital rule, you need to rewrite this as a fraction, okay? As a fraction. But the question is how, okay? The question is how. Now somehow you just need to be very brutal, okay? You just need to be very brutal. But with one thing in your mind, so the skill here is always keep the logarithm at the top, at the numerator. So what do I mean by this? You have x times log of psi x. Let me insist keeping log of psi x in the numerator. And I brutally push the x at the bottom, like this. But why do I do this? Because once I do this, I get a fraction, okay, f over g, and moreover, this is of infinity over infinity form. Infinity over infinity form. Then becomes L'Hopital. So let me apply L'Hopital. So differentiate both the numerator and denominator. The numerator, when you differentiate, you get psi x, 1 over psi x, times cosine x. Differentiating the denominator, you get minus 1 over x squared. But as I say, every time you apply L'Hopitals, it's often you will obtain some nasty expression like this. So before I do anything crazy, I will usually tidy this up a little bit. And then, for example, now it will become just minus x squared at the top, and then cosine x, and divided by psi x. Of course, you can L'Hopital it again because this is 0 over 0 form. But if you are like me, who don't belong to the religion of L'Hopital, then you can rewrite this as x over psi x times cosine x. The reason why I do that is our best t come back, psi x over x, the limit is 1. So minus 1 times 0 times 1, so the answer is 0. I was marking one of your questions from the semi-final, and then I discovered some new mathematics. Just a remark, okay? Kind of relevant and irrelevant, okay? Remark. Limit psi excuse me, this is not 1, okay? This limit equals to limit of h go to 0, h sine x 1 over h should equal 0 by squeeze theorem. And don't think I trapped you, because I think there's a question in the homework 3 that tests you an identical trick, okay? I forget which question, okay? C, homework 3. About this, please, okay? Because to apply your best t, you need to make sure that the guy in the middle has to go to 0. However, as h go to 0, 1 over h does not go to 0. So you cannot apply your best t here. Don't abuse your best t. That's the point I want to make. Okay, so we discussed two variants of indeterminate form, infinity minus infinity, and 0 times infinity. We discussed 3 more. They are all relevant to powers, okay, or exponent. So there are 3 more what we call indeterminate powers. So let me put a star here. 5 star, okay? So the 3 indeterminate powers, they are 0 to the 0, infinity to 0, and 1 to infinity. So I want to make 2 remarks here. Remark. So these are the only 3 indeterminate powers. Any other combinations are not indeterminate powers. For example, 1 to the 0 is just 1. or 0 to infinity is just 0. So these are not. Shut up, okay? Why? Indeterminate powers. So for example, a standard example is if you have the limit x to the power 1 over x, and then x go to 0 plus, the answer, you can read that directly as 0. Because it is of the form 0 to the infinity, and then this always equal to 0. You don't need to do anything fancy like what we're going to do next. Okay, remark number 1. Remark number 2 is related to this guy, 1 to the infinity. That is, I think you know what I want to write. 1 to the infinity is not necessarily 1, okay? Because, for example, we have learned a famous limit, that is the limit 1 plus 1 over x to the power x, x go to infinity, that equals to the number e, which is not 1. But just now I make another joke in the other class. I always wonder how people teach it in Zhongwen, because you want to say that it's not 1 is yi, but then in Zhongwen there will be 不是一但是一, okay? And then it would go insane. So how people teach this in Zhongwen, I'm wondering. Yeah, it would be very funny. Okay? It's not yi, but it's yi. Okay. Okay, let us deal with an example, okay? So limit x go to 0 plus of x to the x. So this is of the first indeterminate form, that is 0 to the 0 form. And the way to deal with indeterminate powers, okay, let me put down the skill here. The skill is to take logarithm. That is always the trick that we use in this course wherever we handle exponents that are complicated. But I will do it slowly with you, okay? So let y to be the limit that I'm interested in, x to the x. Then if I take logarithm from both sides, then of course I will get log of y equals to log of x to the x. But why do I want to take logarithm? It's because, okay, I want to abuse an advantage of logarithm. That is, I can move the exponent to the front. So I will get log of y equals to x log x. But what we are interested in is not it's not y, but the limit x go to 0 plus. So let me take limit on both sides. But the point is, now the right-hand side becomes something a lot more manageable. In particular, using the trick that we learned just now, whenever you have x times a logarithm, that is so-called 0 times infinity form, you rewrite it as a fraction, and then bear in mind that you keep the logarithm at the top. And then the reason why we do this is now you obtain a fraction that is of the form infinity over infinity, L'Hopital. So when you differentiate both the numerator and denominator, you get 1 over x and then minus 1 over x squared respectively. But of course, if you tidy this up, this becomes just minus x, which becomes just 0. Okay, but we need to be careful, okay? We're actually not interested in the limit of log y. We are more interested in the limit of y itself, okay? Limit of y itself. So how do we do that? Well, because log is continuous, continuous. That means that I can shift the limit inside the bracket to obtain log of limit x go to 0 plus of the function y like this. Okay, this is what we learned in week 2. Whenever you have a continuous function, you can push the limit inside the bracket. If you can't see it, I can draw the bracket for you. So what happened is, I start with log of something, okay, log of something equal to 0. That means, difficult mathematics. That means this guy equals to what? If log of a garbage equals 0, what does garbage equal to? What? Log of garbage equals 0. Garbage equals to 1, correct. Equals to e to 0, which is 1. So we are done. So don't forget this step, okay? But in the past, a lot of students will just write 0 as the answer, then we deduct 1 mark, okay? So 0 is not the final answer. Be careful about this. 0 is not the final answer, but log of e to the 0 is the final answer. Okay, let me do the next one. The limit x go to infinity of the limit 2 to the x plus 3 to the x plus 5 to the x to the power 1 over x. So before I do anything crazy, I should identify whether these indeed are indeterminate form. So this is our x go to infinity. So here, x go to infinity. Then the guy in the middle, obviously, we get to infinity. And then the exponent will go to 0. So good, this is one of the indeterminate form, the second one. Then we're going to apply the usual technique. We're going to let y to be the expression that we want to deal with. That is 2 to the x plus 3 to the x plus 5 to the x to the power 1 over x. Then if you take logarithm from both sides, okay, you get log of y equals to log of 2 to the x plus 3 to the x plus 5 to the x divided by x. And now what you're interested in is not just taking logarithm, but you are interested in the limit x go to infinity. Okay, x go to infinity. But why do I do this? Because now I have a fraction, okay? I have a fraction. So I can apply the L'Hopital rule if it's really of the form infinity over infinity or 0 over 0. But in this case, I get infinity over infinity. So by L'Hopital, then if I differentiate both the numerator and denominator, I get the denominator is 1, the numerator is messier. Is firstly, when you differentiate logarithm, you get the reciprocal. But that's not the end. You have to multiply it by whatever, by the derivative of whatever inside the bracket. So differentiate 2 to the x, you get 2x log 2. Differentiate 3x, you get 3 to the x log 3. Differentiating 5 to the x, you get 5 to the x log 5. Firstly, when you divide by 1, nothing happens, so you can forget about it. So you're really dealing with x go to infinity of this nasty limit. But it's not that bad because in week 2, okay, when we deal with limit, when x go to infinity, we have learned a trick. The trick is to identify the dominating term. In this case, okay, you have 2 to the x, 3 to the x, 5 to the x, 2 to the x, 5 to the x, 5 to the x. So the largest term is 5 to the x. So let me divide both the numerator and denominator by 5 to the x to obtain, okay, firstly, I get 2 over 5 to the x log 2 plus 3 over 5 to the x log 3 plus log 5 divided by 2 over 5 to the x plus 3 over 5 to the x and then plus 1. So I divide both the numerator and denominator by the dominating term. But why do I do this? Because as x go to infinity, all this fraction, okay, all this fraction power becomes 0. So at the end, you get simply log 5 over 1, which is log of 5. But remember, okay, remember, this is not your final answer. So hence, the final answer should be x go to infinity of the limit y. It's not log 5, but e to the log 5, which is 5. That's the answer.